All right, so welcome to the lesson on motion of a charged particle in electric field, So last lesson for the electrical part, or the middle third of this unit. So what I want you to be able to do, I want you to be able to determine the properties of motion of a charged particle in an electric field. So let's take a look. So let's recall Newton's second law, the easiest part of the note. That's just your FU law. If we look at it, excuse me, if we look at the situation of two similarly charged particles, so we'll go positive and a negative, keep it simple. That wouldn't be similarly charged, so let's make them both positive. I'm going to lock one in place. So this guy over here, we're going to lock him in, and we'll call it fixed. All right. What information can we get from that? Well, we know we have a distance r, and we know since the one that's fixed is going to be applying, it's going to be pushing this particular particle away, the one on the right. So this is where that electric force is going to be felt or applied. So when we look at this situation, the net force in this situation, or the unbalanced force, Fu, comes from the electric force because the particle is in a frictionless environment, which means that it is Q1, Q2 over R squared. All right. So nothing earth-shattering at this point. I'm not really going to shatter much in this particular note. So the unbalanced force is calculated from Coulomb's law, already taken care of. We can rearrange Newton's second law. So what I'm going to do is, and this is where it gets minor mind-blowing, is what I'm going to do is I'm going to rearrange Newton's second law. We're going to combine Newton's second law, Fu equals ma, with the Coulomb's law. So I'm going to rearrange it. So acceleration is equal to unbalanced force divided by mass. That being said, we just said the unbalanced force is electric force from Coulomb's law. So the acceleration of a particle is going to be K Q1 Q2 over the mass multiplied by R squared. So I'm going to put a box around that. I'm going to put a star here because there is something that's slightly a problem, if you want to say a problem with this formula. Every time R changes, for every moment in time, this length R will change, okay? It's continually changing, which means that our acceleration then is continually changing. So this, what I want to put here is just that A is constantly changing. So that means that if you want to calculate the acceleration or the unbalanced force, you need to know exactly what situation or where you are in the particular, in terms of distance from the two sources and so on and so forth. So it makes it very difficult to analyze particles in sort of real-world applications. So we're going to have to take a bit of a twist on this, and that's where the things get a little bit more exciting. So instead, if we forget about force for a second and we take a look at energy. So we're going to go back to our conservation of energy. So what do we know? That we know that the total energy ET1 is equal to EE1, which is equal to, and we're going to assume repulsion here. So those forces are all equal, and it should be in that space there, K Q1 Q2 over R. Okay, so that is from our energy formula. So the energy in the system, the total energy in the system, so conservation of energy states that it's going to be KQ1, Q2 over R from our previous lesson on energy in a system. So as we move through then, we know that there is a slight change. There's a transfer of energy from one form to another. So we are going to have our total energy after the particle's released. So up here, ET1 refers to particles set in place. There's an energy between the two particles. ET2, I let go of it. There's going to be still some stored electrical energy, but now we have some kinetic energy. All right, so this is up here is the before. Down here is going to be my after. So what's it going to look like? Well, we're going to have our energy So that's going to be K, Q1, Q2, R2 now. Up here was R1, the starting location, plus our 1/2 mv squared. So now we're talking about a velocity. I'll put the vector sign in there so we don't mistake it for voltage. All right. Well, the total conservation of energy says that ET1 has to equal ET2. So we're going to set them equal to each other. So maybe scroll this up so it's a little easier to see on the computer screen. So before all the energy was stored as electrical potential energy, oops, I put it over 2 over R1. Then when we let that particle go, it transforms into still some electric potential energy at a new location plus kinetic energy, 1/2 mv squared. So we can leave that formula in that format. So this is probably a formula that you'll need for the homework. But I'm going to take it a bit further. I'm going to clean it up or change it, manipulate it a little bit to be a little bit more, to create another form of equation for us. Okay, so I'm going to bring and put all the energy on the same side. All right, so I'm going to subtract the K, Q1, Q2 over R2, and that's going to equal 1/2 mv squared. So I'm just manipulating the equation. On the left side, I have K, Q1, Q2 that are common. So we're common factoring out those. That leaves me with 1 over R1 minus 1 over R2. Now, where have we seen that formula before? Okay, previous day, we talked about the change in potential energy, and that is the exact formula for the change in potential energy, except the only difference, if you take a look, for those that notice, the difference is these two guys are backwards. So it was R2 minus R1 the other day. So we can change that mathematically, 1 over R2 minus 1 over R1. But how did I do that? I changed the signs of those two terms. So that means I took a negative out. I factored out a negative to get it to suit what I want, 1/2 mv squared. And now I can replace that with the negative change in electrical energy is equal to 1/2 mv squared, which gives us one other formula. And you move that negative to the other side if you want. But so the decrease or a negative change in electric energy is transferred into our kinetic energy, 1/2 mv squared. So I just did a bit of a manipulation. So let's take a look at how that's going to look or how that works. So two small conducting spheres, so that just means two charged particles, if you want to think of it that way, placed on insulated air pucks. So that means that it's going to be a frictionless surface. One is anchored, the other is free to move. So it's the exact scenario we just talked about. The mass of each sphere and puck is 0.15 kilograms, and the charge on each sphere is 3 times 10 to the 6th and 5 times 10 to the negative 9 coulombs respectively. The spheres are originally at 0.25 meters apart. How fast will the free sphere be moving when they are 0.65 meters apart? So we want to know a velocity, and we have a whole ton of information. So we know, I'm just going to write it down the side here. So we know mass, M1 and M2, even though we only need the one mass. That was in kilograms. We know that Q1, 3 times 10 to the negative 6 coulombs. We know Q2, 5 times 10 to the negative 9 coulombs. We know that R1 is 0.25 meters. We know that R2 is 0.65. And we're looking for a velocity here. So there's only going to be one formula that contains all that information. And I think I'm going to use the original, the first red, actually, I'm going to use the first red box, but I'm going to use the kind of mutated form. I always like this particular form myself as well, just because it's all factored out, a little easier to do with the calculator. So it doesn't matter which format you use, they're all going to give you the same answer in the end. I like this one because it's it matches up with the other one, the R2 minus R1 equals the 1/2 mv squared. So you can do your substitution or you can rearrange, doesn't matter. And I know people won't like it if I rearrange first, but I'm going to anyway. So I'm going to isolate for V. So that means that I'm going to multiply both sides by 2 and divide by M. So I end up with 2k q1 q2 over m, 1 over r2 minus 1 over r1. That's equal to v squared. So while I'm at it, let's get that taken care of. So there's my formula for velocity. Now I can just simply do my substitution. And like I said, you don't have to do it this way. You can plug the numbers in whenever it suits. To the ninth, my q values, 3 times 10 to the negative 6, 5 times 10 to the negative 9, over the mass, 0.15. And then we have 1 over 0.65 minus 1 over 0.15. And now it becomes the fun challenge of being able to enter it into your calculator. And I end up with, or at least when I tried it, 0.07 meters per second. So you want to double check that, making sure that you can actually get that calculation, or make sure you know how to use your calculator, I guess, is the challenge here. So final velocity is 0.07 meters per second. So much more efficient, or much easier for us to do it in terms of energy, conservation of energy and momentum, rather than forces, just because that acceleration is continually changing. A lot more calculations involved. Energy makes it a little bit more simpler, easier to deal with. So I need a little bit more time, so I'm going to finish this off with a second video, and then let you go ahead and try the work from there.